Good morning.
Right. Only 18 members are there. Shall we start? Ravi?
Yes, sir.
Only 18 members are there in the previous class also.
Yes, sir. At the end of previous class also, around
Same.
18.
Okay.
Yes.
Then we will start now. Just I will revise the previous topics in the unit 1. Can you see my PPT?
Yes, sir.
Yes, sir.
Just confirm me whether it is moving or not. It is moving?
Yes, sir.
Yeah.
Yes,
Okay.
sir.
Okay. Thank you. Yeah. From the starting onwards, I will just revise. If I have two classes, continuous classes, then derivation I have to derive in one go. Okay, we can't break because in the last class I have derived one equation. Okay, there are four equations which I need to take in a single go. Otherwise, you can't understand the derivations. So I will just revise the topics which I have covered. So these are the contents. You already know what are the contents involved in the first unit. So in the introduction, what is the mass transfer, basic definitions and various expressions of concentrations like molar concentration, mass concentration, mole fraction, mass fraction. Okay, whereas velocities, fluxes, two types of fluxes with respect to arbitrary coordinates, with respect to stationary coordinates, and how those velocities of the reference coordinates are defined, like mass average velocity, molar average velocity, and volume average velocity. Then next we have seen a Fick's first law of diffusion. The basic law which governs the mass transfer operation is known as Fick's first law of diffusion. Then afterwards, we just derived the relationship between various fluxes. Okay, two fluxes, JA and NI, we just derived using this using the various. Sorry, I will mute everybody. Yeah. Okay, then we have derived a continuity relationship between fluxes. Na is equal to Nxa plus Ja. So from this equation, we used the facts of mass balance, output minus input, rate of mass output minus rate of mass input plus accumulation is equal to rate of mass generation. So using this mass balance equation, we just derived a continuity equation, dou ux by dou x plus dou uy by dou y plus dou uz by dou z is equal to 0. That is nothing but a continuity equation. Then afterwards, in the molecular, in the diffusion itself, there are two types of diffusion. One is molecular diffusion and anti-diffusion. As per your syllabus concern, only molecular diffusion we need to handle. Okay, the first part out of this is molecular diffusion in laminar flow. Okay, in laminar flow we have to handle. In laminar flows, there are two types of derivation. One is A through non-diffusing and equimolar counter diffusion. Then for these two cases, there are two further cases, one in liquid phase and one other one is gas phase. Then afterwards, mass transfer in the turbulent flow, or we can say in the convection, like in a heat transfer convection, we are involved with the heat transfer coefficient. Like in the case of mass transfer convection, we involve mass transfer coefficients here. Okay, you have to see various mass transfer coefficients. It is very easy when you understand this part, molecular diffusion part, that four type of derivation, you can easily just derive these derivations, mass transfer coefficients. Okay, then next phase is interface mass transfer. Okay, in the interface mass transfer, there are primarily, you can say, four theories are there. One is the film theory is there. This the extension for the film theory is two film theory. Okay, first we will discuss what is the film theory. Next, we will discuss what is penetration theory and surface renewal theory. Then how these three theories will differ, we will discuss. And after this, the two film theory. It is a very important theory, which is a resistance theory. So from this one, the relationship between overall mass transfer coefficient and individual mass transfer coefficient, like it is same similar to your heat transfer, in which overall heat transfer coefficient is related to individual heat transfer coefficient. Like that, in the mass transfer in two film theory, we have to relate the overall mass transfer coefficient to the individual mass transfer coefficients. Okay, we have to study this theory part. This is largely a theory part, not a big derivations are involved. Only two film theory is a big derivation. Other three theories like film theory, penetration theory, and surface renewable theory is a very like a theory. Only theories it is. Two, three equations, small two, three equations will be involved. Okay, whereas two film theory is a big derivation is involved. Here, if you know this part, the four big derivations are there. I will say in a easy how to derive it in easy manner. Then, if you understand this part, then only you can understand this part. Okay, this is the what called relationship between various parts of this unit. Then next one, then you already know what is the mass transfer. Mass transfer is nothing but a migration of species or a material from one concentration region to higher concentration region. So heat transfer. Similarly, we can analogously say that heat transfer is nothing but a transfer of heat from higher temperature to lower temperature. Okay. Similarly, transfer of mass is from higher concentration to lower concentration region, or from a one homogeneous phase to another homogeneous phase. Okay, whether there must be a phase transfer or there may not be a phase transfer. Okay, depends on the what type of mass transfer we are handling, whether it is having a phase transfer or whether it is not having any type of phase transfer. For without phase transfer, we can say examples of without phase transfer mass transfer is nothing but adsorption, we can say. Yeah, adsorption. Okay, the solute in the liquid can be transferred directly to the solid phase, so on the solid adsorbent. Whereas in distillation there is a phase transfer is there, because we are just supplying a heat and enriching the vapor content, liquid content with a vapor content with a liquid continuously. So there is a phase change, liquid to vapor. So this is the examples of phase transfer, mass transfer with phase transfer, phase change, and mass transfer without phase change. Then mass transfer is a complex phenomena because it also involves a heat transfer. Okay, heat transfer is a single part where we can't handle, we cannot incorporate. But whereas mass transfer is a complex phenomena because heat transfer terms also involved in the mass transfer. So the advanced part, we can say mass transfer is nothing but an advanced part of heat transfer. Okay, we need to handle these all the unit operations or unit processes present in the mass transfer operations with the utmost care. Okay, because heat transfer, mass transfer coefficients are involved. At the same time, fluid mechanics terms are also involved, velocity terms are also involved. So this is the combination of heat transfer, mass transfer, and together with the fluid mechanics and mechanical operations also. Okay, all these subjects will come into the mass transfer operations. So we need to carefully handle these operations because they are very complex. Then this occurs through a different mechanisms such as molecular diffusion. We can directly relate this to the conduction. Okay, molecular diffusion in heat transfer, we say conduction, convection, radiation. Three type of heat transfer modes are there. One is conduction, convection, and radiation. Okay, similarly here see molecular diffusion, we can say it is analogous to the conduction. Okay, whereas convection in heat transfer is similar to the convection in mass transfer. So here in the convection phase we will relate the we will derive mass transfer coefficients. As in the heat transfer, we will derive in the convection, we will derive heat transfer coefficient. When there is a exchange of temperature between two different fluid phases, then we have to go for the convection. Similarly, when there is a exchange of mass, then we have to go for the convection mass transfer. Where when convection we used to handle, then convection mass transfer coefficients we have to handle. In molecular diffusion, diffusivity DAB is enough, like conduction in the heat transfer K. Conduction in the heat transfer, which is denoted by small k. Okay, which is called thermal conductivity. Similarly here, the mass transfer, molecular diffusion is similar to the conduction in heat transfer. Therefore DAB, diffusivities of A through B or diffusivity of B through A. Okay, anything we can use DAB. We already proved one derivation based on this. DAB is equal to dBA. Okay, then molecular diffusion is related to conduction in heat transfer. Okay, otherwise due to some eddy what you call eddy diffusions which are taking place because of agitation. Okay, you might have seen in the mechanical unit operations how agitations can enhance the overall mixing process, agitation process, everything. Okay, similar is the case with turbulent mixing. Okay, when turbulent mixing is there, the mass transfer will take place with higher rates compared to the simpler molecular diffusion. We already given an example of salt. When we mix a salt in water, salt in water and under normal conditions, normal Na2CO3, some complex salts in a water, it will take some of the years to in order to transfer that salt completely into the liquid. Okay, we will take some of the years when we are handling that process to a molecular diffusion. Whereas when we keep some agitation speed, then within hours that mass transfer operations could be completed. So this is the same. You already cleared what is the diffusion, what is the molecular diffusion, what is the mass transfer, eddy diffusion. So we can say the diffusion is nothing but a transfer of a components in a mixture from a region where its concentration is high, nothing but a high concentration region to the lower concentration region. Okay, mass transfer processes can take place in gas or vapor or in a liquid. Okay, any type of phases the mass transfer operations can be taken place using the two mechanisms called a molecular diffusion. One is due to this random velocity of the molecules without intermingling, without interacting with each other. Okay, therefore the mean free path between the particle to particle is very high. As you have seen in the sedimentation, maybe you are going to see in the mechanical unit operations, there is a what we call free settling and hinder settling. You can assume that molecular diffusion is nothing but a free settling, whereas hinder settling is nothing but a eddy diffusion. When we create analogous between mechanical unit operations and this mass transfer. Okay, in mass transfer, mechanical unit operations, you will see what is free settling, how the particles will freely settle in the liquid, and hinder settling, how the particles will just interact with each other and settle in the sedimentation process, which is called hindered settling. Okay, when we compare the mechanical unit operations, we can compare that molecular diffusion is analogous to the free settling in the mechanical unit operations, and when we compare mechanical unit operations with the mass transfer, the hindered settling is nothing but a heady diffusion in the mass transfer. Okay, in the similar fashion, we can understand these three subjects: heat transfer, mass transfer, and mechanical unit operations. Okay, this is interrelated. All these subjects are very much interrelated. Okay, as you can see, I already this is a twin bulb in which the particles, see here, the red particles will have a higher concentration, whereas here the in the left hand side, the particles which are given in a green will have a high concentration. So according to the definition of mass transfer is higher concentration region to the lower concentration region. So when we remove this partition, just the mass transfer, this is a higher concentration, the particles of green will migrate towards the right, and here, since the red particles are in higher concentration toward the right side, so this will migrate to the red side. Base depends on their depending on their intermolecular forces. Okay, depending on their intermolecular forces, how these particles are attracted to each other depends. When you remove a partition, see, the red particles will just migrate to the green side or LHS side, and green particles from the LHS side is migrated to the red side. So overall, until it reaches the equilibrium, equilibrium is nothing but equivalent of chemical potential of these particles. Okay, this chemical potential of each particle should be in a equivalent. Then these particles will interchange with each other in the two bulbs. Okay, this is called a diffusion. This is a clear example for the diffusion case. Okay, whether it may takes place in the molecular diffusion mode or it may takes place in the eddy diffusion mode, depends on the particular forces which are acting on the particles. Okay, then various mass transfer operations are there. We already discussed this one. The first one among gas phase to the liquid phase, like a solvent. Okay, so this is categorized as a gas to liquid process. Okay, the solute present in the gas will just get transferred into the liquid or a solvent which is in a liquid form. Okay, this is called absorption. Okay, you can remember this is absorption. Okay, another operation is also there, adsorption. Okay, we will discuss this later. Then next one is the extraction. Okay, extraction is the usual phenomena. We will refer to the liquid extraction process. We can see in the common terminology, we can say extraction of oil from the oil seeds. Okay, that is also a extraction, but that is a solid liquid phenomena. Okay, usually in the industrial terminology, that extraction process from which the solute from the solid is extracted is called a leaching. Okay, that is a leaching process. The solute in the liquid phase is extracted, which is extracted using the solvent is also present in a liquid phase, is called extraction process. That is called liquid extraction process. Okay, in the industrial terminology, this extraction process is simply, it can be referred as extraction or it can be referred as liquid extraction. Whereas the transfer of solute from a solid to the liquid phase is called leaching. Okay, from the solid to the liquid phase is called leaching. The usual example for the absorption operation is NH3 plus air mixture, which is being transferred, the NH3 separation of NH3 plus air mixture using water. Okay, in which NH3 from the air mixture will transfer to the water is called absorption. Okay, NH3 separation from the air mixture is a clear example for the absorption. Whereas here, see, extraction. Okay, extraction, we can see the many fermentation processes. Okay, in the fermentation processes, we have to separate alcohols from the liquid phase to the using some other fermentation drugs. Okay, that is the example of extraction, like penicillin separation. Okay, pharmaceutical, in the pharmaceutical industries, penicillin separation, we can give an example for the extraction process. In leaching, we can give the example of extraction of oil from the oil seeds. Okay, you will see this process in the CT2, chemical technology 2 operation, in which how we can extract the oil from the oil containing, oil bearing seeds like groundnut oil. We are using in cooking oils, like all are being extracted from the groundnut oils, palm oil seeds, everything. Okay, everything will be extracted from the solid phase to the liquid phase. Okay, how this solid phase to liquid phase transfer will happen depends on the solute. Petroleum fraction solutes like propane, hexane is used to extract the solute or oil present in the solid phase to the liquid phase. Okay, then next one is the adsorption. Okay, adsorption is the transfer of a solute from the fluid phase, whether it may be liquid or a gas. The solute present in the liquid or gas is being transferred on the surface of the solid is called adsorption. Okay, so, the common example for the adsorption process is we can say dye removal. Okay, dye is present, dye solution in the textile waste is present in its liquid form. Okay, dye is dissolved in the water or some solvents. Okay, we need to separate the dye components from the respective water. We need to add some what we call carbon, activated carbon like this. Okay, so this is the clear example in the water filtration also. When some dye component is there, when we just add some carbon black or some activated carbon inside it, the dye particles or the contaminated particles, the solid particle will absorb those contaminated particles and release the pure water. Not almost pure water, it is free from that whatever the adsorbate is there. Okay, so the dye removal is the example of adsorption process. Then membrane separation. Okay, the transfer of what we call the in the membrane separation, the particles which are larger than the diameter of that pore, a membrane pore, is called a retentate, which will be retained on the surface of the membrane. So it will called a retentate. The particles which are less than that pore size of that membrane will just pass through it, which is called a permeate. Okay, so retentate will be which the particles which are retained on the surface of a membrane is called retentate. The particles which transfer or which diffuses through the membrane is called a permeate. Okay, so the simple example is the filtration of water. Okay, is the membrane separation of process. Then we can see in the tea preparation. Okay, you will just use filter. Okay, some screen or some filter. Okay, it is the process of membrane separation only. Okay, then next one is humidification process. Okay, addition of humidification process is nothing but addition of water vapor to the surrounding liquid, surrounding gas or a surrounding air is called a humidification process. So it is a addition of water, means water is present in the liquid phase, so it will be vaporized. Then only we can add that to the surrounding air. So it is the transfer from liquid to vapor. Then evaporation. Evaporation is nothing but large volumes of water which are present together with a solid particles or just solid or liquid particles just gets evaporated. Okay, very large amounts of water. Okay, we will just give by just giving a heat to the particular solution. We will just evaporate the water present in that liquid. Okay, then crystallization. Crystallization is nothing but a saturation of a liquid, saturation of a solution. Okay, up to the point where it will just crystallizes. Okay, so heating the solution up to the saturation point at which the liquid will be converted to a crystal. It's nothing but a crystallization. Okay, then drying. Okay, removal of relatively small amounts of water present in the solid materials is called drying. Okay, then distillation is nothing but a separation of a constituent elements or the constituents components from a mixture of components using the based on their boiling points or relative volatilities is called a distillation. So all these operations are nothing but a simultaneous heat and mass transfer operation. So when we handle these operations, we need to adopt all the heat and mass transfer terminologies included. Okay, so these are the various mass transfer operations. Okay, out of this you will deal in the mass transfer one, extraction you will deal, leaching you will deal, the next one distillation you will deal, and diffusion obviously it's a basic phenomena. Diffusion, the first unit is the diffusion, which is a basic all the introduction phenomena terminologies will come into diffusion, and next two chapters are the next two units are the distillation, and third unit is the extraction, fourth unit is the extraction, and fifth unit is the leaching. This is you are going to handle in the you are going to learn in the mass transfer 1, whereas in all the other operations you are going to learn in the mass transfer 2, which probably in the next semester. So now this is the basic law, like in the heat transfer, Fourier's law of heat transfer, Q proportional to dou T by dou X or dou T by dou Y, dou T by dou Z, whichever the spatial coordinate we choose. Q proportional to flux is directly proportional to the temperature gradient there. the where proportionality constant is nothing but a thermal conductivity there, K. Okay, here similarly for Fick's law of diffusion is the governing equation for mass transfer here. So Fick's law of diffusion is nothing but flux is directly proportional to the concentration gradient, whereas in heat transfer flux is proportional to the temperature gradient. Okay, here flux is proportional to molar flux or the mass flux we can define, or molar flux we can define. Molar flux, generally we will take a molar flux. When we define this as a concentration, we will define this as a units of molar flux. When we define this as a in place of Ca we use rho A or the mass concentration, then these flux units will be in a mass flux region. So flux is directly proportional to the concentration gradient, and in which the proportionality constant is dAB. Okay, this is the Fick's first law of diffusion. Fick's first law of diffusion says that molar flux is directly proportional to the concentration gradient, in which the proportionality constant is a diffusivity quotient. The meaning of dAB is A through B. This is the definition of dAB. So here you can see Ja is the mass flux or a molar flux. Okay, when we define here rho A, it will be mass flux. When we define here the Ca, we will define it as a molar flux. Okay, Ja is the molar flux of a component A in the Z direction. Depends on this direction. When this is Z, we will say it's at Z direction. When this is X, we will say this is X direction. So units are mole per meter square second. So dou Ca by dou Z is the concentration gradient, which will have a units of concentration will have a units of mole per meter cube, and Z will have a units of meter. So overall combinedly it will have a units of mole per meter for 4. Okay, Ca is the concentration. C subscript A. Sorry, we have to write here subscript A and J subscript A. This is the concentration of component A, which will have a units of mole per meter cube. Then Z is the distance. This is a small z. So accidentally written capital Z. This is a small z. Z is the diffusion, distance of a diffusion path, which will be measured in meters. So overall, the flux is defined as the rate of transport of species I per unit surface area in the direction normal to the transport. Remember here, see rate, when we refer rate, the units will be second. We are referring per mole per second. Rate of transport of species means mole per second, and unit surface is this one, meter square. So flux is the transport of a species I from unit surface area per unit surface area. Then remember this, already I have given this overall formulas in the PDF file to you. So you have to remember this terminology. We already discussed what are these terminologies. Mass, this is the basic unit. So from the fundamental unit mass, we have to derive what is a velocity. It is a vector. Okay, each component will have their respective velocities, which is denoted by small u's with their respective components in the subscript. Then volume, it will have these components A and B will have a volume, respective volumes whose units are given here, and it will have some molecular weight. These components will have a molecular weight which is indicated with the capital M, and it will have a moles, which is a derived quantity, depends on the mass by molecular weight is nothing but a moles. Similarly, it is a additive property, so Na plus Nb is equal to M by M average. So the components A and B will have their respective densities, which is defined by mass per unit volume. So molar concentration we can define for this component A, component B, which is denoted by Ca and Cb. Then mass fraction we will have a individual mass transfer, individual mass concentration divided by total mass concentration, nothing but a mass fraction. Similarly for the B, and this is additive property, sum of the mole fractions is equal to 1, and mass fractions is equal to 1. Similarly, in a mole fractions we have to define, we have a molar concentration of component A and total molar concentration. Ca divided by C is nothing but a mole fraction of A. Then similarly for mole fraction of B, so this is the additive property. So Xa plus Xb, sum of the mole fractions of the component is equal to 1. Similarly with this case, sum of the mass fractions is equal to 1, and then this will have no units. Then flux we will define, already we defined mole per meter square second, we already defined here mole per meter square second. So flux, there are two types of fluxes, Ni with respect to the stationary coordinate, Ji with respect to the arbitrary coordinate. So this will have units of mole per meter square second, Na for component A, Nb for component B. Then N is equal to Na plus Nb, the overall fluxes is. Then reaction rates are there. Reaction rates we can have a units of mole per meter cube second minus Ra minus Rb. This is used in the mass balance equation. Okay, this has a very limited role to play in the mass transfer operations, whereas this minus RA, this minus RB, we can see in the chemical reaction engineering course. Okay, now fluxes. We already defined what are the fluxes. Nothing but a transfer, moles of species I transfer per unit surface area. Okay, is nothing but a flux. So there are two possible fluxes are there. The first one is Ni, which is denoted by Ni, which is the flux with respect to stationary coordinates. Okay, then Ji is the flux with respect to some arbitrary coordinate. Okay, the definition of Ni and Ji given here. See, in terms of when we refer the flux Ni mass, these units are kg per meter square second. When we refer Ni mole, these units are mole per meter square second. Okay, you have to differentiate this. Okay, Ni mass we are writing means we have to use mass concentration rho I, nothing but the units of kg per meter cube into velocity meter per second. So when we cancel out these units, we will get kg per meter square second. So when we use Ni is denoted with mole, then this is concentration multiplied by velocity. So concentration will have units of kg per mole per meter cube into meters per second. So overall these units are mole per meter square second. This is mole kg per meter square second. Similarly, in the case of Gi, which is with respect to flux with respect to some arbitrary coordinate system. So additionally, we will have some average velocity term u naught here. Apart from this is not there because u naught is 0 in this case. Ni case, this is stationary coordinate system. So u naught is 0 here, Ni case, whereas here u naught will be there. So in the species, I have given a clear example that one sailor is floating in his boat and he is observing the number of fishes in the control volume. So that case is that example is referred to these definitions of fluxes. Two fluxes. You can just refer to the previous videos and you can understand what are these fluxes. Now we have to define this u naught. Okay, in a system there are many species which are moving at their individual velocity, at their respective velocities. Okay, we have to take every time some average velocity. Therefore, when you assume that some fishes are moving in the controlled volume, each fish have their respective own velocity. It will move with respect to its own speed. No two fishes will have a same speed. Okay, every fish has a different speed. Similarly, in the mass transfer operation, every species, every component will have their respective. Yeah, this u naughts we need to define here this u naught. There are three terminologies to define this u naught. The first one among is the mass average velocity, and second one is the molar average velocity, and third one is the volume average velocity. Now to define u naught, the first one is the mass average velocity. How it is defined? Sigma I is equal to 1 to species. That for n number of species we have to sum this product. So rho I into u I. This product is added for the n number of species, then divided by rho I, sigma I is equal to 1 to n. For n number of species, that particular mass concentration needs to be added. So the ratio of the product of density into mass concentration into velocity divided by sum of the mass concentration in nothing but u naught mass, which is the mass average velocity. Similarly, in the case of mole, just instead of rho I, we have to use a concentration terms here, Ci into ui. Similarly, in the case of volume average velocity, we have to use the partial molar volume. Okay, rest everything will be same. Okay, as per your this mass transfer one is concerned, we frequently use these two equations, first one and second one, mass average velocity and molar average velocity. Rarely or almost we can say we will not use this equation in the thermodynamics only. The subject which is there, thermodynamics, we will use this partial molar volumes. Okay, you have to remember all these equations, all the definitions, all these equations. The next one, we have derived the relationship between fluxes, which is the relationship between n and j, whether it may be a molar terms or it may be a mass terms. Okay, when we derive this equation, we get the final form as ni is equal to n into xi plus ja. Okay, this we have derived this equation. A. Na is equal to n into xa. Okay, using this relationship, we have proved that dab is equal to dba. diffusivity of A through B is equal to diffusivity of B to A. Okay, this is the definition. This is the proof. We already derived this equation. This is asked many times in your old question paper. Show that DAB is equal to DBA. You have to prove it one. This one, to prove this one, we have to use this relationship. We have to apply this for component A and component B. Then component A and component B fluxes we have to add. Then using the Na plus Nb is equal to N. Then N and N will be cancelled out. Left out terms will be only DAB and DBA. So we just you just refer to the previous videos, then you come to know how we derive the DAB is equal to DBA. The next one, we have to derive a continuity equation. This is also many times asked in your old question papers. So to derive a continuity equation, we need a mass balance equation. Then what is a mass balance equation? Mass balance equation is saying that rate of mass output minus rate of mass input plus rate of mass accumulation in the system is equal to rate of mass generation inside the system. Okay, this is the mass balance equation using the fluxes in terms of our terminology in the mass transfer. Using the fluxes and velocity, volume and areas, we have to apply in this equation, and finally we will get a continuity equation. Okay, then continuity equations are derived with the assumptions that it is present at steady state and density is constant. Okay, these three assumptions we have assumed in the continuity equation. Okay, no reaction already, no reaction is there. Then next one is the Fick's second law of diffusion. Remember, Fick's first law is the basic definition which is governing the mass transfer. Okay, Fick's second law is the basic equation which is governing the what we call that unsteady state mass transfer. Okay, this is C. This is mass transfer equation which is governed for the steady state. Okay, dou Ca by dou Z for the steady state. And whereas this Fick's second law of diffusion, this is the law which is governed for the unsteady state. Unsteady state means dependent on time, whereas steady state means independent of time. That particular variable is not a function of time, then it is called a steady state. When that particular variable is a function of time, that is called unsteady state condition. So Fick's second law of diffusion is applicable only to the unsteady state systems. So this is also derived using this laws, using this relationship between diffusivities. You can watch the previous videos and you can come to know how this we derive this equation. So this is also based on two assumptions. The first one is the velocity is zero, and second one is the no reaction. Okay, so this is the case. And next, the important derivations. From now onwards, we will see the four important derivations in the one go. So the final derivations we have to derive is this one, which are highlighted in the boxes. So final equations, you will derive this one. How we have to derive this? We will derive in the separate class. So see, for the liquids, I have already given in the word file what are the definitions of concentrations for the liquids. So I will just keep on this word file. In the word file, you can clearly see when the two components, since for the mass transfer, in the mass transfer course, you are concerned only for the two components, not more than two components. So concentration in case of liquids is nothing but a mole per unit volume. Okay, which is equal to the density by molecular weight average. Okay, rho by m average. Okay, this is also from your CPP course. Then see, all these are already defined equations. In case of, see, for the gases, we define concentration in the form of N by V moles per unit volume, which is also equal to the from the ideal gas law, which is already equal to the P by RT, pressure divided by universal gas constant R into T. Okay, for the gases, mole percentage is equal to volume percentage is equal to pressure percentage. These are the formulas we have to remember. These are the facts, not the formula. These are the complete facts. Okay, from this equation, the final equation we have to derive is this one, using the relationship between diffusivities. Okay, this equation plays a basic role. This equation, and at the same time Fick's first law of diffusion we have to substitute here. So you need to remember Fick's first law of diffusion and the relationship between diffusivities. Okay, you have to by heart this one. Okay, one way is to derive this equation, other way is to just remember these two equations. Every equation, every derivation is dependent on these two equations. One is relationship between these fluxes, and next one is the Fick's first law of diffusion. Then see, here using this that laws. So first case is steady state molecular diffusion at rest at laminar flow. These all equations are applicable at laminar flow only in the molecular diffusion case. So in this one, A through non-diffusing B. Then what does that means? A through non-diffusing B means. So A is just diffusing, whereas B is not at all diffusing. I have given the example of NH3 plus air, which is a mixture, which is present in a mixture NH3 plus air. So our task, the primary task is to separate NH3 from this air and NH3 mixture. So in order to do so, the this particular mixture air plus NH3 mixture, we have to diffuse this mixture through the water. Okay, when we are diffusing this mixture through the water, what because ammonia is soluble in water, whereas air is not soluble in water. So here A is diffusing. If you consider A as ammonia, B as air, so in the ammonia and air mixture, the separation of ammonia, only ammonia is getting transferred into the water. So we will consider A is diffusing, but B, which is air, is not at all diffusing. So that is the case of A through non-diffusing B. So Na, some value will be there, some value will be there for Na, flux of A. For Nb, so it is not at all transferring into water, so Nb will be 0. So this fact we have to use in your relationship between diffusivities. In relationship between diffusivities, see here Na in the A through non-diffusing equal to total flux is equal to sum of the individual component fluxes Na plus Nb. Here Na plus Nb we will just put it 0, then this N is also Na N is also equal to N in case of A through non-diffusing B. So this is one case, A through non-diffusing B. We have to remember this fact in the A through non-diffusing B, Nb, the flux of component B is 0. Okay, then this derivation, what A through non-diffusing B case, we have to apply for two derivations. Like for first one is for liquids and next one is for gases. Okay, similarly for the equimolar counter diffusion, same here. See, heading is same, steady state molecular diffusion at rest, laminar flow, but the case is different. Here equimolar counter diffusion. Equimolar counter diffusion. See, when this equimolar counter diffusion will happen. So Na, mm, for example, in case consider mm, what we call NH3 plus some other gases, some acidic gases are there. Like NH3 is a basic gas, SO2 plus S4 mixture is there, sodium, sulfur trioxide, sulfur dioxide, and sulfur oxide. Okay, when these two gases are there in the manufacture of H2SO4, okay, SO2 and sulfur dioxide and sulfur trioxide you can take. SO2 SO2 and SO3 is there, sulfur dioxide and sulfur trioxide. Okay, this sulfur trioxide and sulfur dioxide needs to be dissolved in water. Okay, these needs to be diffused in water. Then what happens? The based on these solubilities, SO2 and SO3 will get equally soluble in water. Okay, SO2 will also compete with SO3 and SO3 will also compete with SO2 in order to dissolve in water, get dissolved in that water. So if you consider SO2 as a component A and SO3 as component B, so both will have a same fluxes. Okay, same rate. At the same rate, it will go into that water, particular water. In that case, what happened? The net flux N is equal to Na plus Nb. So it will be 0 because Na is competing with Nb. Okay, SO2. If you consider A as SO2, B as SO3, SO2 sulfur dioxide is competing with sulfur trioxide. So it will have an opposite sign. Those fluxes or those rates have mass transfer rates will have a opposite signs. So opposite signs are there. So overall flux is nothing but N is equal to Na plus Nb. So Na will be get cancelled. So N is equal to 0. This fact we need to substitute in the relationship between diffusivities here. Same. So capital N, this is N is equal to 0. So Na is equal to Ja. When N is equal to 0, Na is equal to Ja. So directly we can substitute Fick's first law of diffusion here and we can calculate the final these equations. This all these equations will come in a simple manner when we understand this fact that in the equimolar counter diffusion, total flux is equal to 0 and individual flux of component A is equal to negative flux of component B in the case of equal molar counter diffusion. Whereas in case of A through non-diffusing B, the flux NA will have some value. For the component A, flux will have some value, whereas component B will be 0. The flux of component B will be 0. These facts, NB is equal to 0 in this case, and N is equal to 0 and NA is equal to minus NB. These facts we need to remember. Then only we can obtain all these equation in a simple way. Okay, I will show how simply we can calculate this equation, derive this equation. This is until up to now we have covered this portion. So only left out term in the part B. There are three parts in this unit 1. So first part is the definitions. Okay, whatever the definitions I have given in the uh, this word file is the definitions, which is all the first part, including Fick's first law of diffusion, relationship between diffusivities, and continuity equation, Fick's second law of diffusion. All this involves the first part, and part B is nothing but this one, all this derivation. We will see in the next class how these derivations we obtain using these simple facts. Okay, for the next class you have to do only two things. First thing, you have to remember this fact: NB is equal to 0 for A through non-diffusing B, and for equimolar counter diffusion, N is equal to 0 and Na is equal to minus NB. These facts you need to remember. And next one is the relationship, this one. Okay, the two equations you have to remember: Fick's first law of diffusion and this relationship between diffusivities. This is the one task you have to do for the next class. And next task is you have to remember for the A through non-diffusing B, this is the fact: NB is equal to 0, and for equimolar counter diffusion, N is equal to 0 and Na is equal to minus NB. These facts, these two, compulsorily you have to do these two things. Remember all these facts, then only come to the next class. Then I will say in a easy way how we can derive this all these derivations, you can see. Okay. Any doubts until now in the mass transfer, so that we can go easily for the next derivations in the next class. If you have any doubts in the definitions or anything, just ask me now. Okay, from next class we will not have any time to go through the basic terms one more time, so that we can go fast in the derivations. Okay, if you have any doubt, just ask me. Yes, anybody is having doubt? Okay, I'm just showing your attendance. If you have any doubt, just ask me. Please go for the doubts.
Uh, uh,
Hello, hello, Pavani or Ravi?
Sir,
Any doubt? Any
no,
doubt?
sir, no doubts.
No doubt, not at all. Yeah, okay. 33. Okay, based on this attendance sheet only, you will going to get attendance. Okay, the members who are left will not get any attendance. 32 has joined and joined now also she is there. Okay, she will get, and 4 joined. Based on this attendance sheet, you will get the attendance. Okay, just give me your attendance manually once again. 1, number 1.
Present, sir.
2,
Present, sir.
3,
Present, sir.
4,
Present, sir.
5,
Present, sir.
6,
Present, sir.
7,
Present, sir.
8, 8, 9.
Present, sir.
Okay, 9, 9 is not there. Okay, 11,
Present, sir.
13,
Sir.
17, 17, 19, 20,
Present, sir.
22,
Again, sir.
29, 29,
Sir.
32,
Sir.
33, 34. Okay, 34,
Present, sir. Present, sir.
39. Okay, 39, 39. Lost call 39, 39 absent. 49, 49. Okay, 49 is also absent.
సార్
50.
సార్ నేను హ్యాండ్ రైజ్ చేశాడు సార్
హ్యాండ్ రాలేదు నాకు.
చూడండి సార్ పైన హ్యాండ్ రైజ్ చేసిన పైన వస్తున్నాయి సార్ కింద రావట్లేదు పైనకి వెళ్ళండి సార్ చూపిస్తాను నేను హ్యాండ్ రైజ్ చేసిన పైన వస్తున్నాయి సార్ హ్యాండ్ రైజ్ చేసిన
నైన్ది కూడా హ్యాండ్ రైస్ చేసింది సార్ అప్పుడు
నేను కూడా
అందుకనే
హ్యాండ్
ఇప్పుడు
రైజ్ చేసి రావట్లే పైకి వెళ్ళిపోయింది అప్పటికి నెంబర్ కింద కనిపించలేదు హ్యాండ్ రైజ్ చేస్తాను అట్లా
ఓకే ఓకే సరే 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 39 9. ఓకే 49, 49. Okay, 49 absent. 50, 50 కూడా హ్యాండ్ రైజ్. ఓకే, DCT 33.
Present, sir. Present, sir.
రోల్ నెంబర్ ఇవ్వలేదా?
Which is, sir, 33, 17 series 33, sir.
అంటే అందరికి రోల్ నెంబర్తో వస్తుంది ఐడి. ఇది DCT 33 అని వస్తుంది నీకు.
అంటే ఇది లాస్ట్ D10 సార్ ఇప్పుడు
ఓకే ఓకే సరే సరే. ఓకే, I hope you understood. If you have any doubts, just contact me. Thank you.